Welcome to Algebra 1 with Miss Betsy. Today we are going to be completing the square with leading coefficients. This is a method that we're going to use to solve quadratic equations by completing the square when the coefficient of the highest degree variable is something other than 1. So we're going to see that there's a little bit of an extra step that we have to take compared to what we studied in our last video. This is the text that I'm using for my lecture today. It's the second edition of Algebra 1, published by Bob Jones University Press. But it doesn't matter what version you have, it really doesn't matter what publisher, because the process that we use to solve quadratic equations by completing the square, if that quadratic has a leading coefficient that is other than 1, it's going to be the same regardless of who your textbook publisher is. So let's go ahead and dive right into this. This is section 11.5, page 459. And our lame joke for the day: what kind of bees, or lame question, what kind of bees never die? Zombies. Zombies never die. So what exactly is a leading coefficient? Well, we have this quadratic expression here. It's 5x plus x squared plus 6. And you're probably already, red lights going off in your mind thinking that's not the way that should be written. But it is a quadratic trinomial because the highest degree term is second degree. However, you want to order your trinomials, order your polynomials in descending power. So it would actually be written x squared plus 5x plus 6. Let me change this: 2x squared plus 5x plus 6. So we now have this trinomial arranged in descending order of descending power of variable. I can't speak tonight. X squared, x to the first, x to the 0, which is equivalent to 1. This term right here, 2x squared, is our leading term, and the coefficient of that term is the 2. So the leading coefficient is the coefficient of the first term if you have the trinomial arranged in descending power of variable, or it's simply the coefficient of the highest degree term. What we did in section 11.4, when we were completing the square, leading coefficient was always 1. We had x squared plus 5x. We completed that square to say x squared plus 5x plus 5 squared, 25 over 4. We had a regular little pattern that we used to complete the square, and we figured out how to do it. It wasn't difficult at all. But this method of solving a quadratic equation by completing the square only works if the coefficient of that leading term is 1. So what are we going to have to do when we have something that looks like this example here? This is example 1, and we have 4x squared plus 8x, I think. 4x squared plus 8x minus 5 is equal to 0. We want to solve this equation by completing the square. We don't want to try and factor it. So if we're going to complete the square, we put the terms with variables on one side of that equation, and we put the constant term on the other side of that equation. So we now have 4x squared plus 8x is equal to a positive 5. And you think, oh, I know how to complete the square. I take half of this, 8 divided by 2 is 4, and I square it. 4 squared is 16. I'm going to add 16 to both sides of the equation. Well, that's what you would do if the leading coefficient here were 1. It's not a 1. So we have to make the leading coefficient of that trinomial that we are forcing to be a perfect square trinomial, we have to make that coefficient be 1. So only on the left-hand side we're going to factor this 4 out. This becomes 4 times the quantity x squared plus 2x is equal to 5. We've reversed the distributive property by factoring out whatever that leading coefficient is. 4 times 1x squared is 4x squared. 4 times 2x is 8. Well, do I have to factor a 4 out of this somehow and say 4 times 1 1/4? No, because these two expressions here have the same value. We don't have to do anything to that right-hand side of the equation. Now, within the parentheses here, we have something that we can complete the square. So what is half of 2? Half of 2 is 1. 1 squared is 1. So we're going to add 1 to complete the square. Now we have to keep that equation in balance. So are we going to add a 1 over here? Is this what we do? Is our equation balanced? It's not. It's heavy over on this side. But how can it be? Because we added a 1 to both sides, didn't we? Nope, we did not add 1 over here. We actually added 4 times 1. We added 1 within inside the parentheses. However, it's multiplied by 4, so we actually need to add 4 to the right-hand side of the equation, because that's what we actually added here. It just might not look like it to us. Now, we have a perfect square trinomial in the parentheses, and this becomes 4 times the quantity x plus 1 squared is equal to 9. We're going to have to divide both sides of the equation by 4. We have x plus 1 quantity squared is equal to 9/4. Now we have this set up in the form where we can take the square root of both sides of that equation. And rather than do that, rewrite that, I'm going to simply use this marker and say we now have the square root of, good night, square root of x plus 1 quantity squared is equal to plus or minus the square root of 9/4. Go ahead and carry out that calculation, and you have x plus 1 is equal to plus or minus 3/2, because the square root of 9 is 3, and the square root of 4 is 2. Are we finished at this point? No, not quite yet. This becomes x is equal to -1 plus or minus 3/2. -1 plus 3/2 is a positive 1/2. -1 minus 3/2 is a negative 5/2. Now we'll see if my arithmetic is right, because it's really actually quite late, and I don't think it's going to be late. It's going to be correct. Actually, I stopped right at this point. -1 plus or minus 3/2. Your book goes on to complete this so that we have a negative 5/2 and a positive 1/2. We have to complete this to this point either by showing the set notation, negative 5/2 and a positive 1/2, or saying that x can be equal to either 5/2 or 1/2, because this has not been simplified as far as it can go. So that's how you go, that's all you're going to do. It's this one little extra step where you have to factor out the leading coefficient and then multiply back by that same leading coefficient after you have completed the square. So now, let's go ahead and look at our next example. Example number 2. Example 2 says 3x squared minus 2x minus 1 is equal to 0. 3x squared minus 2x minus 1 is equal to 0. We want the variables on the left-hand side of the equation, the constant term on the right. 3x squared minus 2x is equal to a positive 1. We have a leading coefficient that is something other than 1. So we factor out that leading coefficient. This becomes 3 times the quantity x squared minus 2/3 x is equal to 1. 3 times 1 is 3. 3 times negative 2/3, the 3's cancel, and you have a negative 2. Now we have to complete the square. What are we going to do? We're going to take 1/2 of 2/3. 1/2 of 2/3 is equal to 1/3. Then we're going to square it. 1/3 squared is equal to 1/9. So we're going to add 1/9 to complete the square. So are we going to add 1/9 to the left-hand side of the equation as well? Well, let's think about this. We've added 1/9 here, so we should just add 1/9 to the right-hand side. You're thinking about keeping that equation in balance. But we didn't add 1/9. We added 3 times 1/9, which is 3/9, which is 1/3. So you will add 1/3 to the right-hand side of the equation. That's where you can get tripped up in completing the square when your leading coefficient is different from 1. Now, we can factor this perfect square trinomial. 3 times the quantity x minus 1/9 squared is equal to 4/3. All right? I don't think I meant that. I did not mean 1/9, I'm sorry. 3 times the quantity x minus 1/3 squared, because negative 1/3 squared is going to equal this 1/9. And twice negative 1/3 is a negative 2/3 for our center term. Now, we have to divide both sides of the equation by 3. Since we're dealing with a rational number here, we can multiply both sides of the equation by 1/3 instead. And when you carry out that calculation, what you end up with is x minus 1/3 squared, quantity squared, is equal to 4/9. Now we can go ahead and take the square root of both sides of this equation. I'm just going to write it in here. It becomes plus or minus the square root of 4/9. That's funny, this is somewhat similar to the last problem. I have to look at my notes. X minus 1/3 is equal to plus or minus 2/3. Now we're going to add 1/3 to both sides of the equation. X is equal to 1/3 plus 2/3, or 1/3 minus 2/3. So x can be equal to negative 1/3 or a positive 1. Let me see. 1/3 plus 2/3 is 1. 1/3 minus 2/3. Okay. One and a negative 1/3. Okay? Everybody understand that? We've set this up so that we can complete the square. we see that the leading coefficient is not 1, so we factor out the leading coefficient, and we make sure that we do that distribution there so that we add the proper quantity to the right-hand side of the equation. Take the square root of both sides of the equation, get this to the simplest form that we can. Now we have one final problem that I want to go through, and I want to show it to you two ways. First, for those of you who are in my co-op classes, I want you to look at page 461 at the top. There are 8 steps, and it says, solving quadratic equations of the form ax squared plus bx plus c is equal to 0 by completing the square. And we're talking about this the whole time that I'm teaching the videos and I'm explaining what's done, but if you want something that's a concise list, go ahead and look at this. Our final example is 5x squared minus 40x minus 25 is equal to 0. And I'm first going to show you this the way they show it in your book. 5x squared minus 40x minus 25. 5x squared minus 40x minus 25 is equal to 0. We want to put our variables on the left-hand side of the equation and our constant term on the right-hand side of the equation. Now we have a coefficient here. This leading coefficient is greater than 1, so we have to factor out the leading coefficient because completing the square only works when your leading coefficient is 1. So we now have 5 times the quantity x squared minus 8x, and I'll leave some space, is equal to 25. We don't have to mess with this right-hand side of the equation at all because these two expressions here have the same exact value. We complete the square now within the parentheses. 5 times the quantity x squared minus 8x plus 16 is equal to. Now why is it that we have plus 16? Because when you complete the square, you take half the absolute value of the coefficient of the first degree term, half of negative 8, negative 4, its absolute value is 4. You square it to get a positive 16. Is equal to 25, right? No, your equation's out of balance. So we have to add something to this right-hand side of this equation. Well, we add 16, right? Nope. We add 5 times 16, which is 80, so that we end up with a sum on the opposite side, on the right-hand side of this equation, of 105. See if I can keep up with my markers here. 5 times x minus 4 squared is equal to 105. And then we simply complete this work here by dividing both sides of the equation by 5. We have x minus 4 squared is equal to 21. Now we take the square root of both sides of this equation. Again, I'm just going to write the square root in, plus or minus the square root of 21. And I have x minus 4 is equal to plus or minus the square root of 21. 21 is prime, there's nothing else you can do. So x is equal to 4 plus or minus the square root of 21. And that answer is fine as it is because you cannot simplify the square root of 21. You can only approximate it. Now this is the method that they showed you in their book because they're wanting you to understand and to practice the process of factoring out the leading coefficient so that you can complete the square on trinomials even if their leading coefficient is not equal to 1. So I understand why they did it this way, and that's all right. However, you always want to be on the lookout for ways to make your work easier, because we say, you know, mathematicians are sort of lazy. We do things the easiest way that we can. Not that I'm a mathematician, but God gives me the ability to teach some algebra. What should just be screaming at you? Common monomial factor of 5. If we would have divided, factored out of 5, divided by 5, divided both sides of this equation by 5, however you choose to phrase it, you would have had from the beginning x squared minus 8x plus 5 is equal to 0. Friendlier numbers, you don't have to factor out and multiply back again. You simply complete the square. X squared minus 8x is equal to a negative 5. You complete the square by taking half the absolute value of this, which would be 4, and squaring it. And you add 16 to both sides of the equation. And I see that I changed my problem. That's supposed to be minus 5. Minus 5. Which gives us a positive 5 on the right-hand side of the equation. We've added 16 to the left-hand side. We add 16 to the right-hand side of that equation as well. And you now have perfect square trinomial here that you can factor. Becomes x minus 4 quantity squared is equal to 21. You take the square root of both sides of the equation, and you're going to end up with the same exact answer. X is equal to 4 plus or minus the square root of 21. Obviously, you have the same answer. Obviously, the reason they did it this way is they want you to see that you really can factor out the leading coefficient. But don't fall into their trap of thinking you only know how to do something one way. Because if you had recognized that there was a common monomial factor of 5, your work is short, and then you introduce less opportunity for error. Because when you're doing this, it's very tempting, right? It's a trap there where you will add the wrong quantity to the right-hand side of the equation if you're not careful. So that's the end of completing the square with leading coefficients. Work as hard as you can on it. If you get stuck, send me a text, and I'll see you next time.